This section is on finding areas of regular polygons. So first of all, a regular polygon is one in which all the sides are congruent and all the angles are congruent. We'll have to use some certain shortcuts along the way of about 45, 45, 90 triangles and 30, 60, 90 triangles. And we're going to revisit this topic later in the year once we learn some basic trigonometry. For now, though, we're confined to certain types of shapes. We're only given a little bit of information, and we can do more shapes if we're given more information. So I'll do some examples after going through some vocabulary. The area formula for a regular shape, area is 1/2 times the perimeter times the apothem. Half PA, 1/2 perimeter times the apothem. Perimeter is the distance all the way around. The apothem bisects one of the sides. So here you see the apothem is this segment and bisects this side and makes a right angle. That's important too. It goes to midpoint, makes a right angle. A radius goes from a center to a vertex, and so here's the center. So you get, with an apothem and a radius, you get a triangle in here. And an important thing to realize is that you'll have many triangles in each polygon. So this is a hexagon. It's got 6 sides, and so we see there's 2 triangles per side when you split it up this way. So I can go ahead and draw these in. So there's always 2 per side, and because there's 2 per side, in this case there's going to be 12 triangles. There's 360 degrees around a single point, so if you do 360 divided by 12, you get 30 degrees. So whichever number of sides there are, you double it to get the number of triangles. You divide it into 360 to get this angle. And once you know that angle, then we can look just at this one individual triangle here. And if we find the area of the one triangle using half times base and height, where the height is the apothem, the base is half a side, and multiply by the number of triangles in the entire polygon, we can get the area that way as well, besides doing the half perimeter apothem. They end up being equivalent. Okay, so here's an example. We have a square, and our radius is 5, and because there are 4 sides here in the square, there are 8 of these triangles, 2 per side. So we do 360 divided by 8 to get 45 degrees. That means this is also 45, so we've got a 45, 45, 90 right triangle. We have the long side. To go from the long side to a short side, you divide by radical 2, and so this would be 5 over rad 2 as well. And then this one triangle that we have shown here is going to be 1/2 times a base of 5 rad 2 times a height of 5 rad 2. And if you want the area of the entire square, you've got to take the one triangle times 8, because there's 8 of these triangles in the entire thing. Let me draw that for you one more time. See, we have 2 on this side. We have 2 over here. So 1, 2, 3, 4, 5, 6, 7, and here's the 8th triangle. And so 5 times 5 times 8, 25 times 8, rad 2 times rad 2 is 2, and this all simplifies to an area of 50, which would be square units. If we had some sort of unit like inches or feet, it'd be square inches, square feet. Okay, equilateral triangle. So there's 3 sides, so there's 6 of these small triangles, and so 360 divided by 6 is 60 degrees. This time we're given a radius. If that's 60, we know this angle here is 30, so we've got a 30, 60, 90. We've got the long side. To go from a long side to the side opposite the 30, the shortest side, you divide by 2. To go from the side opposite the 30 to the side opposite the 60, you multiply by radical 3. So you may need to revisit your triangle shortcuts. So the area then is 1/2 times a base of 5 rad 3 times a height of 5. And there's 6 of these triangles in the entire thing, and that simplifies to 75 rad 3. Just as a quick review as we're going along, here are the triangle ratios for 30, 60, 90, 1 rad 3, 2, and for 45, 45, 90, 1, 1 rad 2. Okay, back to the polygons now. So this is our triangle. Let's take a look at a regular hexagon. Regular hexagon, 6 sides, and so there are 12 of these triangles, so 360 over 12 is equal to 30 degrees. And so this is 30 degrees, so that makes this 60. To go from the side opposite the 90, which we have, to the side opposite the 30, you divide by 2. To go from the 30 to the 60, you multiply by radical 3. And so the area of the entire thing is 1/2 times a base of 2 times the height of 2 rad 3 to get one triangle, and multiply by 12 because there's 12 triangles in the entire hexagon, and this comes out to 24 radical 3. Okay, square, triangle, and hexagon are the only ones we can do currently with this given information until we get to trig. But if we want to do other shapes, such as an octagon, we just have to be given more information. And a regular octagon wouldn't look exactly like this, but we can use these numbers anyway. So we have the apothem and we have this base. We could either do the half times base times height times the number of triangles, but I want to show it this way using the half perimeter apothem. So if this is 3, we know that the entire side is 6. And the perimeter then is 6 here times 8 sides, so our perimeter is going to be 48. So then the area is half times p times a, so half perimeter apothem. So 1/2, perimeter is 48, the apothem is 10. This comes out to 240. So the half perimeter apothem, it always works. I just prefer generally to go with the triangle method, if possible. All right, some more examples over here, different parts of these problems. Okay, in this problem number 4, you are trying to find the values of these angles. And so it's again this idea dividing by how many triangles there are. Now, for angle 1, there are 8 of these triangles in the big one. So 360 divided by 8 is going to be 45 degrees. For angle 2, well, this will be 45, 90, so angle 2 will also be 45. Angle 3 is a right angle. Angle 4, well, there's 4 of these triangles in the entire thing, so 360 divided by 4, that's just 90. Coming over to number 5 here, to get angle 5, there are 6 of these triangles in the entire thing, so 360 over 6 is 60 degrees. That's a right angle, which makes angle 6 30 degrees. Angle 7, there are 3 of these larger triangles in the entire big triangle, so that's going to be 120 degrees. And then over here, to get angle 9, there are 12 of these smaller triangles in the entire hexagon, so 360 over 12 is 30 degrees. To get angle 8, well, there's these bigger triangles, there's only 6 of those, so 360 over 6 gives you 60 degrees. And then to get angle 10, if we just look at this triangle here, we've got 90, that one was 30, so angle 10 must also be 60. There's other ways to get these angles too, just showing you one way. Okay, another example. To do these problems, you always want to have a radius and apothem. So I'm going to draw in the apothem. There's 6 of these triangles, so 360 divided by 6 is 60 degrees. That makes this 30. To go from the 90 side to the 30 side, we divide by 2. 30 side to 60 side, multiply by radical 3. So one triangle is a half times base times height, and there are 6 of those triangles in the entire thing. So that'll be your area. That half and 2 cancel, and we get 12 radical 3. And then a few more problems. Now, these couple of problems, we can't use the method we've been doing, because what happens is this is an octagon, and so there's 16 of these triangles, and so if you did 360 divided by 16, you get 22.5, which is not a special triangle ratio, ratios that we can use. And so that's why we would need the trig if we didn't have more information. Luckily, we have more information, so we'll use the half perimeter apothem method. So 1/2, now the perimeter is going to be, each side's 5, and there's 8 sides, so 5 times 8, and the apothem is 6, so this ends up being 20 times 6, which is equal to 120 inches squared. Now for this one here, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 sides. So we'll have 1/2. The perimeter is going to be 9 sides times 4.7 times the apothem, which is 6.5, and that will come out to inches squared. So you have to multiply that out, and again, your area is always in units squared.